So first quick vibe check. Who here has never used crypto? Don't be shy. Awesome, many of you. Who here thinks that crypto is also maybe a little sketchy? Literally all of you. This is great. This talk is exactly for you. I titled my talk Blazing Fast Magic Beans because I work on Solana, which is the fastest, highest throughput blockchain. And this is the description of the cryptocurrencies section on lib.rs. It's very funny. I'll give you a moment to read it. But essentially, it says that many applications of cryptocurrencies are questionable. And personally, I agree. In fact, if you ask me, I don't even work on a blockchain. I work on a financial transactions database. I am Alessandro. I work for Anza, and I am part of the performance team working on Agave. Agave is the fastest Solana validator client. Before getting involved in Solana, I created Aya, which is an eBPF library for Rust. Solana uses eBPF. That's how I got involved. Aya allows you to write kernel programs in Rust itself. So in order to do that, I added support for eBPF to the Rust compiler. At Solana, we want to build the platform that will power what we call the internet capital markets. We want to put all the assets, all the markets on one network. Unlike it is today, you have separated markets and you need a very expensive license to play. We want to build one permissionless network where anyone can participate. And one quick note, permissionless does not mean lawless. This is key. A lot of people here, I think, think that because it's crypto, it's going to be illegal, it's going to be scammy, Ponzi. No. Permissionless means that everyone can participate, but there are still laws. Laws still apply, okay? This is a slide from Syndica, which is a company that, among other things, does analytics on blockchains. And as you can see, in the first half of this year, exchanges running on Solana generated more than 1.2 trillions in volumes, okay? Perhaps more importantly, in the same half of the year, the applications deployed on Solana generated more than $1.6 billion. This is impressive, especially if you consider that crypto is a new industry and that many of those companies are very small startups with like a handful of people that started weeks to months ago, okay? And to give you a bigger picture of all the applications deployed across all the blockchains, applications deployed on Solana generate nearly half of the revenue. So how does this work? Effectively, it's a spicy distributed database where time is divided in 400 milliseconds slots. Leaders in this cluster rotate. Each leader gets 4 slots. While a node is a leader, it will receive transactions. It will schedule and execute them. At the same time, streaming will stream the transactions to the rest of the cluster. The nodes that are not leaders will replay the transactions. They will apply the state transitions, and then every 400 milliseconds, they will vote on the final state of a block. When the cluster reaches consensus, then that becomes part of the blockchain. This was supposed to be a video, but this is the PDF, so I cannot show you. Oh, yeah, it works. So you can actually see this is a live view of the cluster working, and you can see the leaders rotating every 4 pulses, every 4 slots. They change, and they rotate across the whole world. The main concepts in this distributed system are transactions, programs, and accounts. Transactions can invoke programs. The programs, they can read and write from accounts. The programs themselves are the on-chain programs. What runs on the blockchain is written in Rust. It's pure Rust. It's not a DSL. It gets compiled to eBPF. Then we have a user space virtual machine that will JIT the eBPF code. All the code, all the access to resources, disk, memory, whatever is expensive to execute, gets metered. So the more you want to execute, the more you have to pay. We call this compute units, and it's very similar to how many clouds work. This is also how WASM works if you enable fuel metering in WASM. And then finally, the programs they execute, they do some changes to these accounts, and then if a transaction doesn't get rolled back, the changes are committed. Accounts are essentially a glorified key-value store where the keys are public keys, and the data, the actual documents that you store in the database are just arbitrary sequences of bytes. In order to make changes to these documents, you need to prove that you own the documents. So you need to sign the transactions with the corresponding private key to the public key. An exception is that programs themselves can create and modify accounts. This allows for some great abstractions. But because obviously the programs are deployed on chain, they cannot be holding any key material, so there is a separate ownership access model for programs. Importantly, accounts are read-write locked. So this is important because parallelization works around this concept. So if programs are all reading one account, those programs can be executed in parallel, but whenever a program starts writing to an account, it's guaranteed to be the only program doing writing that account, which makes the security model a lot simpler. Transactions are sent and received using the Quick protocol. Clients can either target the leaders directly using Quick. Each transaction is a stream, so they can send streams to the leaders. Or if you're sending, for example, from a browser that does not have the technology to send quick streams, we have these special RPC nodes that will receive JSON RPC requests, and they will relay the transactions to the leaders. This is some example client code. It's very similar to how you would build an HTTP request. At the top, we say, OK, we want to do a transfer from this address to this address, and we want to transfer this amount of tokens. And then you put this instruction in a transaction, sort of like an HTTP message, and then you send it to the server. This is what an on-chain program looks like. You can imagine that it's like a Rust binary crate. Instead of having a main function, it has an entry point. It's literally the elf entry point to the program. And it will receive the accounts that the transaction specified and a bit of instruction data. The instruction data is kind of like a query string in an HTTP request. It's an arbitrary piece of data that the client and the server can pass to each other. And usually a program based on instruction data will route in the same way that a web server would route on a resource or a query string. The programmer will say, OK, the user wants to do this. In order to do this, I need to read from these accounts, and I'm going to write to these other accounts. Now I'm going to show you some really cool things that we do with Rust. We do a lot of open source. I'm going to show you some of the things we do. In the last year, we've been doing this huge push to improve throughput of the cluster in an effort that we call Increased Bandwidth, Reduced Latency, IBRL. We use Quinn as the crate to implement Quick. We've been doing a lot of contributions there. We implemented GRO support, UDP GRO support, in order to in order to skip some kernel overhead in receiving a lot of packets. We do very high throughput ingestion when a node is a leader. On the client side, we implemented a new strategy for sending streams, sending transactions, that reduces fragmentation a lot, which also reduces latency. We're trying to create a very low latency system. And also, we greatly reduced memory allocations done by Quinn while ingesting transactions. All the crates using Quinn will benefit from these changes. And we are currently doing some work to reduce contention. The biggest problem Quinn has is contention between the I/O crate, Quinn UDP, and the protocol parsing crate, Quinn Proto. We're working on reducing this contention, and when we're done, we're planning to switch from Quinn UDP to our XDP-based implementation for ingesting datagrams. We recently started rewriting the storage layer to use IOU ring instead of memory maps. We looked around, we found some crates. The existing IOU ring crates for Rust mostly use async. Our system is mostly non-async, so we wrote a new crate that is a wrapper around IOU ring. Purely Rust, no C dependencies. It's very fast. For example, when now you start a node using this new IOU ring implementation, we need to, when we do a cold boot, we need to unpack a 100 gigabytes large tarball. And with this implementation, with this crate, we can do it nearly 3 times as fast as when we were using the regular RS crate. We also started rewriting the networking layer to use XDP to do kernel bypass. So we created a new crate, Agave XDP. This is all open source. This is all on our GitHub. To my knowledge, this is the fastest XDP implementation in Rust. It's based on AYA. My plan is, once the API stabilizes, to move it back to AYA. It supports both SKB, fallback mode, and all the most popular NIC drivers used on clouds or on Metal servers. And it's very fast. So that's a perf stat sample of 10 seconds, while Agave was sending 2.5 million packets per second. And as you can see, in 10 seconds, we generated in total 27 context switches. That's less than 3 per second, which is impressive considering that we have hundreds of threads. And we generated exactly 0 page faults, which is great for performance, right? And also, we have a very high instruction per cycle factor. It's 4.5 on a machine that can do 8 in total, so it's pretty great. Most of these changes were made possible by Solana. It's a new eBPF-based profiler we wrote, completely in Rust. It's a brand new profiler. It's not open source yet. We're planning to open source it soon. In my opinion, this is the best, most powerful profiler for Linux. It allows profiling of CPU code, context switches, disk I/O, memory. For example, if you look at the yellow part on the left, we're doing some rayon operation that is it's calling rayon. Then the caller is waiting for the workers to complete, for the pool to complete the work, and it's sleeping. That yellow part there is taking nearly half of the time, and with a regular profiler, you wouldn't see it at all, because the process is sleeping, and so it's not on CPU, and so a profiler cannot catch it. We can catch it. The profiler also supports custom span markers. So the yellow bands you see at the top there, those are slot spans. So we generate one for each slot. You can attach metadata to these spans. In this case, you can see the number of transactions that we're executing. You can narrow down the profile on that specific span. This helps a lot if you have a slowdown that is happening at a specific time. You don't know why it's happening. You have a large profile, and you want to pinpoint why something is happening. The profiler also supports giving line-by-line profiling. So you can see at the bottom left, for each line, you get a counter, and you see exactly which line is slow, and you also get a disassembly view of the source code. The UI here is profiler.firefox.com. It's a great website, and we're just integrating with it. This is an example of an I/O profile. All the black markers you see at the top are when Agave was doing some disk operation, was not hitting the Linux page cache. Because of that, it was fairly slow. And so we want to debug that, and we want to reduce those disk accesses. There are a bunch of other markers. I'm running on Italian time. Last slide. It's also a memory profiler. This is a DAT profile showing all the allocations done by a process while running. You can get this today using the DAT crate. So you can just use the DAT crate in your program. It will replace the global allocator. It will instrument all the allocations. It works, but it's very slow. In our case, we couldn't use this at all, because when using the DAT crate, the validator doesn't start at all. By using this profiler, we can attach at runtime. Only when we want to instrument, you attach at runtime with eBPF, and you get a profile. We want to compete with the NASDAQ. We created a website called flipd.market, where we show our performance relative to the NASDAQ. Go check it out. This is Kevi, is one of the developers on the Solana ecosystem. A few weeks ago, he was able to push the public cluster, what's deployed publicly, to execute more than 100,000 transactions per second. This is Andrew, one of my colleagues. Just last week, he was able to push the scheduler. He works on the scheduler to execute more than 1 million transactions per second. We're doing a lot of really cool system-level work. As we saw at the beginning, nobody here is working on crypto. If you go on jobs.solana.com, there are more than 500 jobs. Most of those are for Rust people. So please go check it out. Be open-minded. I'm not a crypto person. Before joining Solana, I had never done anything crypto. I'm in it for the tech. We're doing really cool tech. Please join. Thank you.